to the 4th International Webinar on Construction Materials. First and foremost, we acknowledge the Gadigal people of the Eora Nation as the traditional custodians of the country we are meeting today. We recognize their continuing connection to the land and waters and thank them for protecting this coastline and its ecosystems since time immemorial. We pay our respects to elders past and present and extend that respect to all First Peoples Nation present today. The Institute of Construction Materials is a community of experts in the field. We are sharing our experiences and knowledge throughout this platform with a broader international community. The quarterly Journal of Construction Materials, online courses, and the recently developed ICM coin as our crypto asset are only some of the ways that we are helping achieving our goal. My name is Janice. I'm your moderator for this year's webinar. I'm currently working towards a Master of Philosophy in Structural Geology at the University of New South Wales, a study that parallels construction. This year's webinar is mainly focused on topics related to economics, nanomaterials, automation, and of course, concrete. At the end of our webinar, I'd like to invite you to create your account with us if you don't have one already, using the link provided in the chat. I'll send you a link in a separate email as well. This way, you can earn your very first ICM coins. 10 ICM coins will be deposited in your account right after your first login. This crypto asset, which is built on top of the Ethereum blockchain, can help you with your funding, research funding, even internationally, without paying for the exchange fees. Currently, it is valued at $2 each, and we expect it to become available to the public trading forum in the next few years. This webinar is being recorded and will be posted on YouTube. Each speaker will present their recent research outcomes in a 15-minute block, followed by a 5-minute question and answer forum for you to ask your questions. Microphones and video will be disabled during the presentations and enabled during the question and answer sessions. There'll be a 20-minute break in the middle of the webinar between 10:10 and 10:30. We apologize for Ahmad Tabish, who's unable to join us today as per our schedule. Today we'll get started with Dr. Dharma Harage with his presentation, Economic Benefits of Energy Conservation in Modern Construction.
Yeah, thanks very much, Janice. Thanks for that introduction. So let me share my my screen. Just give me a second. Okay, so I'm going to talk about economic benefits of energy conservation in modern construction. As a part of this, I'm going to compare between the old construction and new construction, and look at what are the economic benefits in terms of energy, conserving the energy. This is basically based on a couple of submission in this, a couple of publication in this area. Now, as far as the household energy is concerned, the heating and cooling accounts for about 40% of the household energy consumption in Australia. So what the last the 20-25 years, the space heating has increased by around 12% per house. And we expect this to sort of increase in the coming years because of the climate change, which we are already experiencing. Quite often we have extreme heat wave and also extreme cold wave. So because that both of our heating and cooling is going to increase. I don't think any of us, at least in Sydney, can survive without an air conditioner now. So if you look at the total energy consumption within the house, the space heating is around 40%, and the water heating is around 23%. Appliances like the cooking, the appliances and some of those would include around 30%. And then the lighting is around 7%. So the lighting is a very small fraction of the entire energy required within a house. So the space, the heating and cooling is the main the majority component, which is around 40%. Now we can use some passive strategies for reducing the energy load, particularly on the space heating and cooling. That is, something to do with optimizing the building materials by using higher thermal mass with the floors and walls, and also the better insulation. Now, especially in the eastern part of Australia, building orientation is very, very important. The orientation will help you to save energy, particularly during the winter time. And you need to have an appropriate windows to wall ratio. This is what exactly is mandated by basics in New South Wales. And they need to have a proper glazing, cross ventilation, and shading. Internal and external shading, in order to conserve energy within the building or within the residential house. Now, I think a lot of us are familiar with this NSW, the Building Sustainability Index basics. So basically gives us some credits based on our design of our residential houses. So we need to maximize. We would like to maximize the energy conservation using some of these guidelines. So as you all know, that we need to get the basics certification before we start building any new house. Now, I think it's, when we are doing a designing of a house, identifying the climate zone is very important. Now, Australia has got a different climate zones depending upon the location of where you are. So something like this. So you've got a hot and humid climate on the top end of Australia. Like in the case of Darwin, whenever you listen to the news, you always see around 33 degrees centigrade, the temperature there. So which is the hot and humid condition throughout the year. And then if you go towards the eastern side of the country, so you'll get into a more of temperate, the conditions, which is the cool weather, and also the very, very nice weather conditions for better living, I suppose. And along with that, you have a well-defined, the seasons, the 4 seasons. So during the winter time, you would like to have some heating arrangement within the house. And during the summertime, you will have some cooling arrangement within the house. So the heating and cooling comes into picture on the eastern side of, Australia. So you got different weather conditions across. As you know, Australia is a big continent. So we've got different weather patterns depending upon where you are in Australia. What we did was we did some. We sort of created different scenarios with different building materials, and we sort of simulated some of these scenarios using an energy simulation package, which is called EDA-EYES. So using EDA-EYES, we simulated what is the heating and cooling energy requirement across all 4 seasons, summer, winter, spring, and autumn seasons. So we sort of compared all those energy requirements. We sort of created about 10 scenarios. So for each one of them, we worked out what is heating and cooling requirement. So the materials what we looked at were, some of these old, low thermal mass, the buildings, which include the Fibro house, raised timber floor, and Fibro house with better flooring, where we considered, some kind of tiling of the flooring system. So we included this old type of Fibro houses, and then some new constructions, which include brick veneer, reverse brick veneer, and double brick walls. So we divided all those into about 10 scenarios. So we consider what is known as PSEEDS. So PSEEDS is passive solar energy efficient design strategies. So which basically includes, the orientation to north, particularly for Sydney, and also, the internal, external shades and double glazing and some of those things. So we analyze with PSEEDS and without PSEEDS. So with PSEEDS means we have got all these passive solar design strategies. Without PSEEDS means we don't have those the design strategies. So we sort of created those 10 scenarios, and then we simulated all those 10 scenarios. Now, what exactly mean PSEEDS? Now, the PSEEDS is passive solar energy efficient design strategies. So house with PSEEDS and house without PSEEDS. So house with PSEEDS we consider as an improved house, which includes a double glazing, and then with a certain U value there, and orientation northern, shading devices, internal integrated window shading devices, and also the ventilation. Means we are assuming here that the houses with PSEEDS have low level of leakage of air into the house. Whereas on the other side, we have got a house without PSEEDS, so where you have got a single glazing system. Here again, we are still looking at northern orientation. No shading devices are used yet. And the normal infiltration means there is quite a bit of infiltration of air into the house. So here we are looking at 0.5, and here is 2. That's almost 4 times higher. So there's quite a bit of air leakage in these houses without PSEEDS, and also all the glazing is a single glazing system. So that's a difference between the house with PSEEDS and the house without PSEEDS. Now, when we simulate the energy requirement for all these 10 scenarios, so the blue one is for the cooling energy requirement, and the red is a heating energy requirement. You can see that in the case of the standard houses, standard houses means without the PSEEDS, you can see that there is a bit of energy requirement in terms of heating. Whereas if you go for improved houses where we include PSEEDS in the design, so the heating requirement is pretty much very, very low. So that is what has been picked up by this software. So the energy requirement for heating can be drastically reduced by incorporating some of these passive solar design strategies. And also we can see that the Fibro houses have got a higher energy requirement compared to something like a improved the brick veneer and double brick houses. So in fact, I think the reverse brick veneer has got the lowest energy requirement in terms of both heating and cooling. Okay, so that gives again this is the totally done by energy simulation using a package called IDA-ICE, which is which is sort of developed by a Scandinavian country, and we have done a few studies in Australia using this particular software. So looks looks reasonable to me, these results. Now, what we did was we also looked at the economic cost of these designs. We did the economic value of energy consumption over 50 years time. So we are considered, for the next 50 years, if you're going to continue with using HVAC system, that heating and cooling system for each of these houses, for the next 50 years, what would be our net present value? So net present value means we are considering the the interest rate on these the cars, the energy cars, and using the interest rate, we work out what is the net present value of all those investments which you're going to do for the next 50 years towards paying a bill, towards paying the electricity bill. So out of all that, for the next 50 years, improved sort of improved reverse brick scenario is has come out to be the lowest, around 78,000, and a Fibro house without the PSEEDS, that's the passive solar design strategies, has come out to be the most expensive, that 250,000. So it's almost 3 times the total energy cost for next the 50 years. And if you look at the improved reverse brick the scenario and the improved Fibro scenario, here in this case we have got the reverse brick house and Fibro house there. Between those two, again, there is almost 2 times difference. So does this indicate that we demolish one of these Fibro houses and build a new house? Yeah, so this should give some kind of incentive for people, if they're looking at, although it will not be able to recover the entire money of constructing a new house, at least you'll be able to save some money on energy consumption. So again, a lot of these, the calculations we are done based on the current energy cost or energy rates. These energy prices can change. So in the next 50 years, the energy price maybe is double what we have now. So because of that, it would be super economical, I suppose, to build to demolish existing Fibro house and then build a new brick veneer house. So there's some the cost offset we can get by reducing the energy cost with a new modern construction. We also did some real life comparison. So we got 2 houses here. One was at the same place. We had there was a Fibro house, and that has been replaced with a brick veneer house. So we consider this as a case study, and we looked at the based on the electricity charges for both the houses. We sort of compared the electricity usage per meter squared per day. So for the winter, spring, summer, and autumn. So you can see that winter and spring, there's quite a bit of reduction in the electricity usage for the modern houses. if you're looking at kilowatt hour per meter square per day. So that does indicate, there is, the saving by going with, the new modern construction compared to the older houses. And we looked at the overall, the savings in the electricity usage. So old fiber house was 31 per, the kilowatt hour per meter square per year. And the modern brick veneer house was 23 kilowatt hour per meter square per year. The saving was almost 35% there. So in conclusion, so it means both the real data and as well as the simulation data seems to indicate the modern brick veneer houses can save between 35 to 50% in energy consumption compared to fiber houses. And we'll be able to achieve, this is the reduction in the energy consumption that will result in, cost saving in the energy bills. And I'm sure these savings will increase as the power bill, the rates, the energy rates are going up. So it will make a sense, to some extent, to replace the old fiber house with new brick veneer house. Again, this is only based on the economics, but we haven't really considered the environmental issues yet. So environmental issues, the reducing the energy consumption can result in, the carbon emission reduction as well. And there will be, more comfort in living. There's a social benefits, there is an environmental benefit and social benefits, which, if you consider, it definitely stacks up about using, modern construction to replace our old building. There are a couple of these, the papers we have published on this. I think, you can access some of these, I suppose. Okay, that's all I wanted to say. Happy to take questions if there are any.
Okay, I'm just gonna let everyone unmute and start the video, and we can start question and answer time.
Okay, can I ask a question? So there are two tables, Dr. Hagara, I've found. One was for the net present value of the, was it for the savings or was it the cost associated with implementing those environmental actions?
Yeah, so in that, so let me just share.
The scenario number 5 had the lowest amount of net present value.
Mm-hmm.
And I was wondering if it helps in the savings, or is it actually a cost accrued?
Is a cost. It's a cost. See in this one. Can you see my table?
Yes.
Yeah. So in this, what we have done is we have considered the cost of the energy cost for the next 50 years, and also in the case of PSEEDS, that's the passive solar design strategies. We have also included the cost of implementing the shading devices and double glazing and some of those things.
All right, so this is actually going to be added to the final value of a property if we're about to save some energy.
Yeah.
Is it correct?
Yeah, that's right. So in the case of the improved reverse brick, the reverse brick veneer house, so the cost of energy for the next 50 years is $78,000. And whereas in the case of the standard Fibro house,
Second scenario.
it's 250,000. So
the
the
highest.
difference between those two is basically because of high energy costs in the case of Fibro house.
Yeah. Thank you so much.
Thank you. Mm-hmm.
do we have any more questions today? You can either type it in the chat, or I've made it so participants can unmute and start their video during question and answer time. Otherwise, I can turn this over to Isaac for his presentation, financial risks of public-private partnership projects in the era of COVID-19. So Isaac, if you can start your video and start sharing your screen. Hi, Isaac. Beautiful.
Is it okay?
Yeah, we can see you can start.
Okay. Good morning. My name is Isaac Akomia from Pong. I'm at Western Sydney University. I'm presenting on managing financial risk of public-private partnership projects in the COVID-19 pandemic or the era. So I'll be presenting these things to you this morning. Introduction, problem statement, aim and objectives, research method, results, and then my conclusions. So public-private partnership is a model which has been widely accepted in the construction industry. And the public-private partnership is simply a collaboration or a partnership between the public sector. The public sector here, I mean the government, I mean the central government and local government and the private sector. Many years ago, most of the public infrastructure projects were normally executed by only the government. But for the past, I would say about 30 years or 20 years, we have seen the involvement of the private sector in helping the public sector, which is the government, to execute these projects. And the commonest or the common features that we can see with this model of executing public infrastructure projects is that normally the private sector and the government, they share the risk. And then also normally the profits and the losses that will come out of the project, they also share them together. So as you can see here, for the past about 30 years, and from this World Bank data, you can see that there has been a rise or an increase or acceptance of this model in developing public infrastructure projects, especially in the developing world, where it is very difficult for governments to get finance to support their infrastructural projects. However, since the COVID-19 pandemic, this issue of government getting money has gone up or has become very difficult. The reason being that during the COVID-19 pandemic, we have all seen mandatory lockdowns, shutdown of projects, delays and missing of deadlines, social distancing, and mental health issues, as well as health and safety tools. All these things have led to an increase in the way projects were executed in terms of the finances and the losses that come out of projects. And some of these things show or attest to the difficulties that many countries are encountering right now in terms of the COVID-19 cases and the deaths. And as you can see from this slide, as of 21st of June 2021, these are the cases and the deaths of the COVID-19 pandemic. And these things have really affected projects in terms of increasing the cost of executing projects. So in this study, what I did or what I went through is that I decided to find out what are the key financial risks or what are the key financial losses associated with PPP project, especially in this COVID-19 pandemic. And then I also wanted to find out the measures that we can put in place in solving these problems. And then even the ones that maybe 20 years from now, 100 years from now, or so many years from now will also come. So the objectives or the aims and objectives of this study is to analyze the financial risk of PPP projects in this COVID-19 pandemic. And then the two objectives are to identify the critical financial risk of PPP projects in this era. And then the next thing is to highlight the control measures for practice and future research on financial risk of PPP projects. So this is the research method I use. Basically, I use a 3-step approach. The first step was that I did a thorough review of existing studies or literature review. And the literature review, I limited the studies to 2020 and 2021. So as of June 2021, I got only 32 articles relating to this study. And then I did some content analysis. And out of that, I extracted some key variables and statements from these literature. Literature were taken from Scopus, Web of Science, Google Scholar, and PubMed. So the second step was that I designed a survey, an online survey, because of the social distancing and you can't get access to people physically. I did an online, or I designed an online survey. And this online survey, I collected a number of emails. I'm talking about PPP experts. I sent these emails to them with the links, and then I made them answer the survey. And then after I collected all the survey, I did a factor analysis in PCA. I must say, or I must confirm that this study is still ongoing. So these are, I would say, the initial results that I'm going to present. So it's still an ongoing study. And then I showcase the results. The results, I group everything into 3 using a factor analysis. I'm talking about the financial risk, economic factors, environmental factors, and the social factors. So this is the results out of the study. The descriptive analysis showed that these are some of the authors who are contributing to this study. That was the literature review. And you can see some of the names here, Abechan, Oseche, and then other people who are into this study. And then the institutions where I sent the survey, and then also where studies are being conducted on PPP projects, financial risk, and the COVID-19 are some of these institutions. As you can see, Western Citizen University, Kwame Nkrumah University of Science and Technology, Hong Kong Polytechnic University, University of Technology, Sydney, UTS, and others. And then these are some of the countries. So these are the countries where studies are being conducted. And these are also some of the countries I also sent the survey to. So Australia, China, Ghana, and other countries. So out of the analysis, this is what I've been able to discover. So the results show that these are the critical financial risk of PPP projects as far as the COVID-19 is concerned. The first one is the interest risk. According to the experts, the interest risk of PPP project has gone up. The reason being that because of the COVID-19, some of the loans and some of the capital that they contracted to construct this project, they have not been able to finish the project because of the delays and then the setbacks. And therefore, projects which were scheduled to be completed and then start operating, so that people or those who, I'm talking about the project managers, will get money out of the projects. Those projects have not been completed, therefore increasing the interest risk. In other words, the interest risk is supposed to be, they contracted the loan for, let's say, 5 months or 10 months or 2 years or 3 years. And the projects are supposed to be executed by, let's say they take it 10 months and the project is supposed to be executed within the 10 months. But here is a case where we have a pandemic, and for the past about 18 months, some of them, they have not been able to even gone back to work on the projects. Therefore, the projects have not been completed, and then the financial charges are still there, which I don't know how, or they don't know how they are going to get money to finance this. Then also construction costs, they have also gone up. The reason being that inflation rates and then other issues relating to the construction materials, they have also gone up. Then cost overruns have gone up. Health and safety costs. We all know how the COVID-19 has increased the health issues and then the health related costs of construction workers. And then even there are also instances where it is very difficult to get even money to start projects, because it seems the whole world is in economic crisis. So that was also one of the challenges that they highlighted. And then termination, of course, there are even situations where the project they have to terminate the entire project entirely. So that's also another thing that I discovered from the experts. These are some of the control measures that the experts proposed that going forward we can put in place in order to solve some of these problems. One of them is to design an effective cost management strategies. And then also to assess project capital, there must be a way or an alternative way of financing projects, not only looking at only the private sector or looking at the government or looking at some international donors, but there must be a broad way of getting access to finance. And then other things that they suggested, as you can see from here. So the conclusion from this study is that from what I discovered, it seems a lot have not been done as far as this issue is concerned, and a few cases which have covered few countries. So going forward, I propose that researchers look at this and cover this issue in many countries. Many countries, I mean, especially countries where the COVID-19 has wreaked havoc. I think that this issue must be looked at. And then poor supervision and risk management should also be looked at. And then limited conceptualization of this issue must also be looked at. The implications of this study is that this study could be a guide for project managers to control financial risk of PPP projects. And then it's also, this study will further studies which other researchers are going to look at. And then policy implications. I think that financial risk, not only I think, but I mean, coming from the discoveries that I got from the literature and then the experts, financial risk is a very prominent issue which policymakers must look at going forward. So they need to, especially relating to health and safety. So it's something that they have to look at and then design policies on them. So I think that's all for today. Thank you very much for the opportunity.
Thank you, Isaac. I've started the Q&A, so people can unmute and start the video if you have any questions. I have a question though. So for your research, you found that only like very few countries have been publishing research about the implications. Do you think it's because of other countries' policies with the public-private partnerships, or it's just really strange that like there's just so few like I guess countries and universities really looking at it, publishing it, and I know it's a really new kind of thing. But you know, the construction industry really drives, you know, the economy, especially, you know, in Australia. It's such a big thing for us, and I know it is a big thing overseas. So it's just so strange that, yeah, when you're saying like was like it's like 6 universities and 3 countries. Do you have any like insights as to why it's just these 3?
Okay, I think it's because the you know, the pandemic it started early 2020. So I believe that as time goes on, like maybe the post-COVID, we'll see so many studies, because I think some people are still looking at waiting for the outcome of the pandemic, the results, because like we are in the middle of the pandemic and we don't really know the results. And you know, when you are in the middle of something, you can assess it very well, you know. So, but when the thing is over, then you can come out with the effects. So I think people are a little bit skeptical, or they are trying to set back, or they are delaying a bit. They want to maybe see the pandemic all over, or when it's over, then they come out with studies or the results, because most studies, or the studies that I read, I discovered that most of the studies are more of a case study, exploratory, and most of them, they say that we are still waiting for the pandemic to be over. So I think that's the reason why we have few universities and few countries where this thing has been done. I think that maybe if we look at the next year or next 2 years, when we are all fully vaccinated and the pandemic is over, then people can really take a very good analysis of the whole pandemic thing. So I think that's the reason why we have few studies from countries and few universities are into this.
That makes a lot of sense. Thanks, Isaac. I think Farid has a question also.
Yes,
Okay.
Thanks a lot for that really great presentation. I had a look at one of those tables that was concluding the financial risk in a COVID era. And the first one, yeah, exactly this one. The first one is interest risk. Now, considering the amount of funds that the government currently, Australian government is currently injecting in the construction projects in terms of subsidies, what is your prospect in the future of the interest rate?
I believe that with the support that the government is giving to the economy, I think that it's in the long run, it will help reduce the effects of the interest risk, high interest risk, especially relating to construction materials, because interest risk and then inflation risk, they tend to affect the construction material. So I think that looking at the way the government, if the government continues to support construction industries and even the entire economy with this money that they are putting in place, I think is going to help to reduce the effects. So that's what I'll say for now.
Thanks a lot.
Thank you. Any other questions?
Okay, thank you. If we have no more questions, I will introduce Farid. So Farid will be, his presentation will be on the electrochemical exfoliation of graphene oxide for use in concrete products.
Thank you.
I'm just going to get this started.
Okay. Do you have my screen?
Yep, it's looking good.
All right. So the topic that I want to present today as Jenny said, is electrochemical exfoliation of graphene oxide for use in concrete. I have to first say thanks to Jenny for narrating this webinar. It wouldn't be really possible to organize this webinar without your support, and of course other speakers who have given us this honor to be able to learn from their latest research outcomes. The topic that I want to present once again is electrochemical exfoliation of graphene oxide for use in concrete products. This was an experimental research project that was done back in 2019 when the laboratories were open without any hesitation. But as you also know, there is a long way from lab to the real world marketplace, although the results might be promising. I'll start by briefing on graphene and its properties, then we'll move on to explaining why do we need this concrete product. I'll then share the laboratory experimentation and the results. My email address is, as you can see on your screen, and I will be more than happy to respond to any of your inquiries, suggestions, collaboration proposals, especially, and also other things that might come in your mind. The first question that I have to explain a bit is what is basically graphene? That is a one-layer thick structure of carbon atoms that has some exceptional crystalline quality in the nanoscale. It has recorded high thermal conductivity, which is beneficiary to the curing process as well. As you might already know, the cement hydration reaction is exothermic by nature, which means it generates heat as the chemical reaction develops. Endothermic reactions, on the other hand, require heat absorption for development, and that's just for a recap. Now, this high thermal conductivity of graphene particles help in cooling down the inner parts of the concrete blocks, especially in the first 3 days when the strength gain occurs. Once the internal heat finds its way outside of the concrete block, the chances of cracking reduces by a lot. In fact, in the traditional curing processes, we spray water on the surface to cool down the block. Relevant literature had reported up to 30% improvement in the compressive strength of concrete reinforced with graphene particles due to the better internal curing process. The next most important question that you might also ask yourself is that why we should put a such an expensive material in graphene, in concrete. It is expensive. And by the way, just so you know, each gram of high quality graphene is priced around $500. And you're going to need 3% addition by the mass of cement for an optimum result. I did a math for you. For each ton of concrete, you will need 10 kilos of graphene. And if you decide to reinforce your concrete with these nanoparticles, that adds up to $5 million for only 1 ton of concrete. And with a 1 ton of concrete, it can only pour a small slab. So it is by no means any viable financial consideration. Nobody does that in a commercial scale, unless stupid, maybe if. But apart from the unviable cost of reinforcing concrete, let me emphasize here more again, with high quality graphene, apart from that, you can think of mechanical improvements and the prospects. We can think about affordability later on in this presentation. And we've actually made some low quality graphene oxide in the lab for a price almost 20 times less. And it can be reduced even further upon commercialization and optimizing the processes involved. So another mechanical benefit is the high electrical conductivity of graphene. And when I'm referring to another mechanical strength, I'm talking about another benefit rather than that curing that I've explained previously. It is indeed being categorized as a superconductor. Now, you might say that this is a destructive property for concrete as it scales the rate of corrosion. And that's a perfect argument that we don't have an investigated answer to. However, thinking of polymer coating of steel reinforcement doesn't look irrational. The major advantage of highly conductive concrete appears when you think about the future roads that can charge your electric vehicles on the go, which is a prospect, even if you look at the state government plans. There have been some initial studies done in Sweden on this topic too. Moving on, we must consider what are the downfalls and what prevents us from getting there. If you get through the existing literature and summarize the outcomes of the several past years, you will end up with a list of problems like this that you can see on your screen that prevents us from further developing the promising graphene reinforced concrete. We've already discussed the first two problems are being costly and the lack of studies around the corrosion rate. Another problem with graphene when it comes to mixing in concrete returns to its hydrophobic characteristics. It just doesn't like to be mixed in water, which causes agglomeration, meaning that it will be seeing chunks of little black balls in concrete. And it's not good because you are expecting a continuous path for both electrical and thermal conductivity and not seeing chunks of black balls. But remember, we have so far talked about graphene and not graphene oxide. Luckily, there is a much cheaper way of producing a material really similar to graphene that is called graphene oxide. Graphene oxide shares a lot of similarities with graphene, such as high compressive strength and both high electrical and thermal conductivity. Then in contrary, however, it is not hydrophobic, and I mean graphene oxide. Rather, it is hydrophilic, actually, because of the oxygen atoms, which means that it not only doesn't create chunks of little black balls, it actually helps in a better dispersion. That continuous path for electrical and thermal conductivity can be achieved by using graphene oxide instead of graphene in concrete. From the comparison between the molecular structure of graphene, as you can see, you can tell that it yields a relatively lower thermal and electrical conductivity than pure graphene because of the impurities that are embedded in its structure, which is both good and bad. It appears to be good for a lower corrosion rate and bad for the conductivity matters. Nevertheless, the major advantage of reinforcing concrete with graphene oxide and not graphene is the affordability of this material, because after reviewing the literature, there has been no significant difference observed between these two in terms of mechanical performance in concrete. So basically, by using graphene oxide instead of graphene, you can save a lot and get the same outcomes from the mechanical perspective. So there are two main methods of producing graphene particles, which I will explain in this table. The first cheaper method that is being used to produce graphene oxide is faster in comparison to the other one. This is the method that we have actually used during the laboratory experiments. The second method is used to produce high quality graphene, which has applications in other industries such as electronics. That's just super expensive. It's not going to be viable by any means for construction application. Electrochemical exfoliation, the options that we've chosen, refers to the process during which the graphite sheets are oxidized in an electrolyte followed by an ultrasonication. Hydrobromic, hydrochloric, and nitric acid plus sulfuric acids are typically used as electrolytes from which sulfuric acid is proven to perform in highest efficiency amongst other acids. So we used sulfuric acid for that reason in our studies. In the beginning of the process, we have lowered the concentration of acid to 2% in this study for exfoliation and also for the safety matters. Starting off with a low voltage for a few minutes from the beginning of the electrolysis would allow the graphite to wet and prepare for proper exfoliation. The voltage applied could be ramped up after a while to speed up the process. The electrochemical exfoliation of the graphite sheets usually yields thick layers of graphene with a small surface areas. However, the modification of the acidity of the electrolyte and the voltage applied can enhance the quality of the final product. I don't know if I'm running out of time. I guess I have 4 more minutes, so I have to speed up. Cathodic exfoliation refers to the process where positive terminal from the battery is connected to the graphite. We have tried this method first, and there was no sign of exfoliation observed after 24 hours with a 6-volt DC current. Even 12 volts input didn't help the process. The reason being probably the sizes of ions in the solution. Once the current is applied to the exfoliation bath, sulfuric acid decomposes into 2 major ions. That is 2 hydrogen and 1 sulfur. This means that in the cathodic process, we've been mistakenly forcing the large ion, which is sulfur, to get between the layers rather than pushing hydrogen, the smaller ion, inside the layers of the graphite. Whereas the more rational way was to force hydrogen to penetrate between the layers. So we have corrected our mistake and switched the positive and negative electrodes. In addition to that, we have tried to test a looser stick with a lower density of 2,540 kilogram per cubic meter. We applied 12 volts DC current again, and this stick had completely exfoliated into graphene oxide after 24 hours. The next step was to excel the quality of acquired GO, that is graphene oxide, via the means of ultrasonication. An ultrasonicator is the apparatus, so that the picture that you see on the left-hand side is exfoliation bath. If we use anodic exfoliation, which means that connecting the negative electrode to the graphite stick, this is the practical way of exfoliating graphene oxide. And the other bath, we had 2 baths in our experiment. The other one was the ultrasonication bath. And an ultrasonicator is an apparatus which shakes the solid particles in liquid solutions using high frequency vibration. Using that, it helped us collecting much finer particles after the filtration. Since we are dealing with nanoparticles in this study, it was important to consider the right choice for the filtration process. The most frustrating step indeed was filtration, as it took the most amount of time in the whole experiment, 3 days until dry particles were ready to collect. So that being said, it opens an opportunity for future studies. And the question that runs that study is to be, what is a better filtration process to speed up the production process rather than spending 3 days to collect dry particles. At the end of the production process, we have managed to make 60 grams of this valuable product available for public purchase. Within the first few weeks that it had become available, we sold 10 grams online to one of our customers through the innovation store. It somehow shows the existing demand in the market. Of course, we are not near to the full-scale commercialization scale by any means, but if you look at the market price and the number of studies done in this area, you can get an estimate about the possible return on investment in case you decide so. The product is recommended to be used only for research and development purposes, as there are still so many areas subject to more investigation. Some of those gray areas that can be noted at this stage are: number one, the quality of the product to be assessed by an scanning electron microscope, or SEM in short. This way we can outline which stage of the production requires more optimization. The number two of that gray list is the process that takes less time to complete. As mentioned, the current process takes 4 days for 60 grams of the final product, which is not ideal. And to wrap up the gray list, we need a proper market evaluation to be done before commercialization starts, i.e. how many customers are thriving to use graphene oxide in their concrete products. And another question that we have to ask ourselves is, does it need government support, or can it be done by a private entity? And of course, many more questions that can come into your mind. Moving on, the concrete mix design. In the next phase of the study, we had made cement mortar samples for electrical resistivity test. The electrical resistivity test had been chosen mainly to outline how good the product is for roadworks. Remember, the future roads are capable of charging electric vehicles on the way. So this table shows the mix design. Graphene oxide had been added to the mix with the ratios of 1%, 3%, and 5% by the mass of cement. We have tried to keep the water to cement ratio constant as 1 to 3. A quick recap is that a lower water to cement ratio directly enhances the compressive strength of concrete, which is always a priority for contractors and builders. The mixing process had been done in accordance with the Australian Standard Code. Cement and graphene nanoparticles had been mixed first, and water was added slowly in the mixer. The mortar had been mixed for 5 minutes, and 4 different samples were obtained at the end, as you can see right here. To get rid of the air bubbles once poured in the mold, the samples had been vibrated for 1 minute and left in a water tank for curing after 24 hours for a duration of 3 days. Another interesting possible area for future studies actually return to this very stage, that is curing, as we are expecting better performance even without curing. But in this study, in order to stay in the safe zone and to avoid any further uncertainties, we managed to comply with the standard codes, especially when it comes to curing. So here are the results. As expected, the samples with a higher portion of graphene oxide recorded a higher electrical conductivity, or in this case, lower resistivity. However, it is not rational to increase the portion of graphene in the mix due to many reasons, the most obvious one being the cost, and the second reason that comes to mind is the uncertainties around the corrosion rate. Regardless, being able to produce graphene oxide is being considered as a technological advancement for the material industry. This was a full summary of what we have done during the past scientific experiment, and I hope that you have taken at least 1 point for your future research studies too. I'll also be more than happy to discuss the future collaboration opportunities with you. My email address for this reason is farid.rtp@iconsmat.com.au, and that was it, yours. Thank you. If there are any questions, I'll be more than happy to answer.
Thank you for that, Farid. I have a question. If anyone else has a question, feel free to raise your hand. I've already started the Q&A session. You can unmute and start your video if you like. My question is that I'm surprised there isn't currently any sort of like industrial scale production of graphene oxide. Is it not used in like other industries, or is it just too new a material? Sorry.
What was the last part of your question?
I was just wondering, is it not currently used in other industries, or is it just like a research tool at the moment?
In Australia, we've got one mass production factory that is in Western Australia, actually in Perth. But the market in New South Wales, Queensland, Victoria, and South Australia is actually thirsty. So I reckon that's a huge opportunity for anyone who wants to invest in this material. And in terms of other industries that had adopted the production of graphene oxide or graphene, I guess electronic industries, mainly because of its superconductivity. So yeah.
Thank you. That makes a lot of sense, actually. But yeah, great investment opportunity. I think Isaac has a question.
Yeah, Isaac.
My question is that how did you capture, or how are you going to capture the cost of this whole thing that you are
With bloods and but
the expenses?
the costs of how big are we talking about? If it's still in the laboratory scale, it is not an expensive process to make 60 grams. Like it costs around 400, 500. It was 2019. I can't remember exactly.
Okay.
But you can sell each gram for, so that covers the costs of production actually pretty much. As for the laboratory scale, of course, if you move on to the commercial scale, the cost will be lower, the returns will be higher. So, yeah.
Okay. Thank you. Makes sense. Thanks.
Cheers.
Yeah, if we have no more questions, we actually have a break until 10:30. So feel free to use this time to either connect to each other or you can just take a break.
Thank you.
Hi, everyone. Welcome back to the webinar. I hope you had a good break during our intermission. I'd like to introduce Habiba. Her presentation is going to be on eco-friendly alternatives as the replacement of cement in concrete. So start when you're ready.
So hi, everyone. My name is Habiba. I am a Master's of Research student in Macquarie University. So currently I'm working in sustainable construction material. So this is my part of my study. So today I'm going to present eco-friendly alternatives as the replacement in concrete. So our first question is what's the concrete? So concrete is basically a mixture of water, fine aggregate, cement, and coarse aggregate. And it's a hugely used material. And due to global urbanization, economic development, and the growth of population, the demand on concrete is increasing day by day. It's more than 10 billion of tons of concrete produced everywhere, and it's the most consumed material after water in the world. So over 70% of all population living in the concrete. So because of its versatile use, workability, strength, durability, longevity, and fire resistance, it's the most usable material in our part. But apart from this, this is also a harmful material for our environment. There are lots of problems associated with the concrete. Like if you say more than 5% of carbon dioxide production, greenhouse gas, it comes from the concrete in all over the world. So we need to do something here so that we can reduce the impact of carbon dioxide. So we are thinking about the use of the raw materials, energy consumption, and water use, reduce them, and use something waste material or byproduct material which are abundant in our environment. It comes from the industrial products, so that we can reduce the impact of the concrete. But if you can see here in the graph, the cement production rate is increasing day by day. And in the cement production system, we are using a high heat system with really consumption a lots of energy, and it uses a huge water, and it generates a lots of amount of waste. So for doing this, my study, it will basically how can you reduce this carbon dioxide and use some industrial byproducts or domestic waste kind of things. So for the make the concrete eco-friendly, our main focus is on using recycling and using waste material. if you look in the Australia condition, it's more than 40% Australian waste goes to the landfill without doing anything. So I define in the 3 waste materials, like is industrial byproduct, commercial, mining, and agriculture operation. It comes from the fly ash, bottom ash, and steel slag. And besides this, we have domestic waste. It comes like a glass, plastic bag, packaging, and it comes through the cleaning, cooking, and repairing empty containers. Even if you overlook here, lots of construction and demolition work is going on in our side. So it also comes with lots of wood, steel, concrete, and plaster. This kind of things we can really implement in our concrete productions and in our manufacture system. In the photo, you can see how all like landfill productions and here everything in the abandoned in the field. So in my first study, I focused on the fly ash, and I really found a good result in here. It's totally abundant from the coal burning power plants, and sometimes it's known as ash speed. And after studying this, I found that it can reduce around like a 20% of cement consumption, and which can really help in to get a better concrete and better environment impact. And even it can, after using the fly ash, I even found it is reduced the amount of water used by 10%. Even using fly ash in the concrete, we can see that it reduced the bleeding. Even it has a very high level of strength, increase the amount of strength. But sometimes in the fly ash, this problem is this wide variety of chemical composition is really help to reduce the how its products is coming. So it's really very vulnerable. Besides that, we have bottom ash, which is also a power plant product and it really goes to the landfill. But after using the bottom ash in the concrete, it really helps to increase the workability, cycling time, and strength. And it can be a good substitute beside of cement. Even for another industrial product, which is the rice producing country, in rice as us, in rice mill, and by replacing the, we can use a 20% of the strength gain in concrete. And to get the optimal, this one can be 20%, and it can be replaced 15% of cement in concrete. We have another industrial product that is silica fume. In my studies, it can replace like a 7 to 12% of cement, and it is a very high strength and it can be durable. Sometimes it's known as micro silica, and it comes from the silicon metal producing manufacturing industry. We have another industrial product that is blast furnace slag. But it has a very good result in than others. It can replace around 70 to 80% of cement, and it has a very improved workability. And in long term, this is a very high strain in compressive and flexural strengths. If this ceramic waste powder as well, it's like a unutilized domestic waste. So it's produced a huge amount and in final polishing system in industry. So it causes a lot of pollution in the soil, water, and air. So, but it has a good improved workability in concrete mixtures, and it can reduce the compressive strength and development required time, but it can improve the durability characteristics of concrete. So, on my another study focus on the waste yard, and this is the most challenging and problematic waste stream in condition of health and environment concern. But it poses a good breeding system for pests, and it's a significant fire hazard as well. So by using the waste in as a crumb rubber as an aggregate, and we can use as a cement replacement as a rubber powder as well. And although it has some reduction in the flexural strength, but it increases the tensile strength as well. So basically, our lots of studies going on here. Even in Victoria, is implemented in the road as well. So kindly, I'm studying on here as a life cycle assessment. So my result hasn't got. So another, lately I focused on the construction and demolition waste. It's the wood ash. So in like construction and demolition, we got a lot of wood, which is, but if we wish, we can use this one as a partial replacement of cement. And you can see here in that it gets a really high compressive strength. And I was thinking to use as a cement powder as a in concrete. It is recyclable, and it is a really good strength. Even we got as the same similar kind of result and as a cement powder. So my conclusion goes through here. We need to reduce the amount of Portland cement so that we can use a lots of supplementary materials. So can we use a lessened amount of cement, and you can lessen the amount of raw material, and we can use more highly recyclable material in it. If anyone interested to collaborate with me, please contact, and this is my mail address. Thank you. If you have any questions.
Thank you, Fibro. That was really great. Oh, sorry. Go ahead.
Yeah, so thanks, Janice. Thanks, Habiba, for presenting this paper. It's pretty cool. Can I have a question regarding the wood ash? How we can use it as a supplementary material, or you can say supplementary cementitious material? I think the wood ash, it's almost the one is in, yeah, and the last one, 14 or 13, yeah.
It's basically like construction and demolition waste, the wood. So we can, this recycling process, we can make it the ash, like after burning, I think. We can use the wood as a burning in cement, and we are getting that ash. I think from that ash, we can use it.
So basically, it's like a grinding or like
as a energy, it's like a fuel, and after that we'll use that ash as a replacement of cement.
Yeah, but have you got this one from any reference? I mean, do you have any reference for this one, this slide, wood ash?
I didn't really add it here.
Okay, so it's not in the number 16. If you go to the slide number 16, maybe.
Yeah, no, it's not there.
No, okay, yeah. Because we should know whether how like a wood will be like reacting with the cementitious material. I'm not quite familiar with this one, so yeah. Anyway, nice presentation. It was nice brainstorming for supplementary cementitious material. Thank you.
I have a question. So these are like industry waste products. Are they already being collected, or is it something that you're experimenting on for the future uses of, I guess, being in a more circular economy where we can use these?
Implemented, and it's already implemented and already being used. I'm working in like environment impact analysis. I'm just implementing that material, how we can be environmentally benefited, or like how much is the benefit in the reduction of the carbon dioxide.
Oh, okay. So it's already being implemented, but
Yeah,
you're finding, I guess, like the statistical.
Yeah.
Okay, I understand. Thank you very much. Are there any more questions today?
Can I ask one? Okay. Thanks a lot, Habiba. I guess there were a comparison between a few supplementary cementitious materials being fly ash, wood ash, and slag. I've never tried that in a laboratory, and I wanted to ask you whether there is a comparison between the compressive strength gained when each individual of these SCMs, supplementary cementitious materials, are mixed in concrete.
Actually, this is basically my literature like study. I'm working on the carbon dioxide reduction system. I'm working a life cycle assessment.
I see.
So I just study on it. This is how much it can be benefited us. And I got this result, and I am implementing in the life cycle assessment. So I didn't really carry out this experiment.
Okay, is there any like quantitative comparison between these in terms of CO2 reduction?
That's what I wanna do. I wanna mix up I wanna make lots of like a computer mix, and then I will see the which in like material is giving the more beneficial result in it to reduction the carbon dioxide.
Okay.
So I haven't got my results yet.
Okay. Thanks a lot.
Thank you.
Really informative.
Thanks for that presentation. I think it's really important that we looking towards going towards a circular economy. It's something that the Australian government is already working on. I think it's a really topical presentation, especially since the National Plastics Plan only came out this year, and how we're all working towards, working towards a circular economy, reducing our waste materials. Thank you very much, Fibro.
Thank you.
Okay. Shitiwan, Doctor, are you able to start now? We're right on time, actually. 10:50 was your allotted start time.
Yeah, thank you so much, Janice. Yeah, we can start right now, I think.
No problem.
So I'll share my screen if I am host or co-host. So start, yep. So here it is. It has been shared. You can see my screen right now.
Yes, it's very good. Thank you.
Yeah. So basically today, my presentation is on the reinforcing cement mortar with the glass fiber. So in inkjet 3D printing technology. So this technologies has been evolved like since 1993, something around that time, like from MIT University. So this, according ASTM standard, American Society for Testing and Material, additive manufacturing can be divided to 7 categories, or classified into 7 categories, which is VAT, photopolymerization, material jetting, binder jetting, powder bed fusion, sheet lamination, and directed energy deposition. So each of these, it can be used for construction purposes. But the one is I'm talking today on it, it's binder jetting, which has another name. It's called inkjet 3D printing technique, or they can call powder bed 3D printing. So basically the 3D printing technologies is how it based it, it's like a layer by layer printing, whether it is in a liquid way, or is it in a resin, or in like a powder. So this technique actually is a layer by layer printing the powder material and dropping the materials like water on it on a specific spot to print the shape that we want. If you see these shapes like a UTS shape or parahouse shapes, those that have been made with a cementitious material and with the 3D printing technology, which is called inkjet 3D printing or binder jetting 3D printing technology. So this process actually takes longer time compared to most of the other 7 categories that I've been mentioning, because it needs a cleaning. So once you finish your cleaning, once you finish your printing, you need to clean it properly until you get your subject or your object. And the powder flowing, usually comes in the back of the printer, which is instead of the paper that we have in a normal printer, the powder is coming out. This is coming out, flowing on the gravity acting and rotating. There is one small rotor inside this, like a bucket in the back of the printer. It helps us to come out the materials properly. It means come out the materials properly from the back of the printer. So if we are thinking in the ones I've been showed earlier in this one, it is usually made by 3D system, which is earlier called Z printer. So now there is some companies like trying to produce large scale 3D printing technology for construction or for other industrial purposes, such as Vauxhall jets. So you have been innovative, the big, like a large scale of the 3D printing inkjet. So, and the layer of this printer, it's larger than the 3D system one. So basically they have been developed this one with the UCLA architectural department in US, and the German, which is Voxeljet itself, is a Germany company. They have been making mini house, something the ones you see on your right photo. So and this can be like a making such a mold in a large scale. Even you can go for 4 meter. This one is a height about 3 meter and 2 meter in a like a length around. So they have tried also to make like a 4 meter houses as well. So because the scale of the printer is around 4 meter size. However, it's not just Voxeljet. There is other companies like X1. They have been using the binder jetting for around 5 years, and this also they have been using for a lot of industrial purposes and manufacturing purposes, such as making the engine or other parts for the automotive. So this is like a general literature regarding the large scale or light inkjet 3D printing, which is applicable for construction purposes. However, there is another printer which is custom made by Enrico Dini in Italy. So he used his printer only for civil engineering purpose, or we can say for construction purpose, which is made like a kind of irregular shapes, which is very hard to make it with our conventional concrete, or we can say like having those formwork that are available for construction. So his companies now is made a D shape, and recently they have been done a lot of works, especially for marine structures. And regarding this work, I just want to show you how we can prepare like a fiber reinforced in a lab, and we can like increase the mechanical purposes or mechanical properties of this material. Usually, if you have a cementitious material, we recommend to mix them once in a one mixer and rotate it for 5 minutes. And during this 5 minutes, we can add in the fiber with a small proportion while mixing. We have been using like a 6 millimeter length of this throughput fiber. And after this one, we have been mixing around 10 more minutes. So it's totally like a 15-minute like a mixing. Why we are adding fiber late? Because we don't want to damage the fiber. As you can see, these fibers on the photo, that's the fibers, all of them easily like mix it without any damage of the fiber. However, the fiber preparations, as I mentioned, it is basically like after selecting the types of the materials and their mixed proportion, the materials were blended homogeneously, and we need to mix around 15 minutes. And usually the speed of the like a Hobart mixer, it's about 1,450. We can go up to 1,900 RPM, but we should consider if it's too fast, maybe damage your fiber. So we should be careful while mixing properly. And regarding the mixing, it's not just the mixing. We need to see the outcomes. So how we can see the outcomes? We should check the surface roughness of the material on the belt chamber and in a printed specimen as well. So what we did, basically, we are being putting these materials like a fiber into the cementitious. Later on, we have been check it with the visual photos or visual eyes. And later on, we have been magnified by microscopy and 3D laser scanning. So once we have been magnified, we see most of the fibers was parallel to the y-axis in the belt chamber of the inkjet 3D printer. So once we have been printed, like we have seen also the materials, which is parallelly about 70 or over 70%. It is parallel to the y-axis. It's less than 30% in a x-axis. So basically, most of the materials in a y-axis, like when we are testing for mechanical properties, it is much stronger. I mean, the bond of the materials is much stronger in a y-axis when we are compared to the other axes. All right. So this is the sees if we are enlarged here, we can see the fibers comes out from the printed specimens. And this test is have been done just for surface roughness. Also, we have been done like a RA. So the RA, which is a surface roughness measurement, we have been using 3D laser scanner to measure how it is look like when we are checking the surface roughness profile. So for the cementitious material with the printed one without glass fiber, we saw about 22.31 like a micron the surface roughness of the material for the printed specimens without glass fiber. But also we have been checked all the profile of the powder bed CP material, cementitious material on the belt chamber as well. It is very high surface and non-homogeneous as well. But when we have been adding this one can be seen in a 3D dimension. This is just like an extra explanation you can see in a 3D dimension. But once we have been adding the 1% of this glass fiber from 22.31 micron, it changes to 18.57. So it means really about 20% the glass fiber improve the material's homogeneity and the surface roughness of the material. If you can see here, you can see the surface roughness of the material. It is quite good compared to the material that is not included the glass fiber in the materials. Glass fiber, it's using usually like a reinforced material, which helps to improve the mechanical properties as well. Here we can see, especially in the compressive, when we have been tested, we got about 37 megapascal. We have been tested similar Q without glass fiber, we got around 25 megapascal, especially in this plane or in this direction, XY direction, because all these materials, when we are printed, they have orthotropic properties. So we have a 3 plane we need to test it on. So we got a different result when we are checking for mechanical properties. However, in a mechanical properties for the printed specimen, for flexural one, we have got that in a flexural as well can be improved, but this improvement it's not really too much compared to the compressive one. So however, in some of them, especially in a lower temperature below like a 70 degrees Celsius, we got very good results with the samples that we don't have a glass fiber. So, but over 18, we didn't see much changes. And that's why we are expecting when we are curing it in like a higher degree of temperature of Celsius. So we should be careful about this mechanical properties of the material. But however, we got like a maximum in 80 degrees of Celsius, but the comparison between with and without glass fiber, it's not too much. Another point we need to check it out, it is overall, all the surface roughness of the printed material, we should be considered because it's really affect the mechanical behavior of the materials. And actually, if we are printing any kind of material with different properties, we get a different results. So basically, because of the cementitious material, it's not just cement. We are using sand and another kind of accelerator. So most probably change the surface roughness. But having a glass fiber with one person, it's really helpful. So I think I highly recommend to be change this ratio to a different ratio. We maybe get different results. So if we are printing this one, the surface roughness of the printed mortar with the 1% of the glass fiber, we have like a 20% improvement in the surface roughness. Also adding 1% of the glass fiber in compressive things will be improved pretty well by 58%, or we can say around 60%. And also the fiber orientation, if we have focused on and using like an image J analysis, we get most of the fibers will be parallel to the y-axis in a powder bed of the 3D printing, of the inkjet 3D printing technique. So this one can be figured out by having actually like an image J analysis. Thank you for your times, guys. And if you have any question, feel free to ask me. This is the end of my presentation.
Thank you for that presentation. I do have a question mainly about, I guess, 3D printing times.
Yeah.
As the technology improves, like, you know, we've all been watching 3D printing over the last, I think, decade, and you know, having 3D printers come into the consumer market and people could buy it for home. Would you say the limitation for this would be the size of 3D printers, or the cost, or the time it takes to produce, really?
Actually, this is a very nice question, Janice, because most of the people was afraid from the cost. But basically, if we don't have competitor, so in a market, if you have a competitor, everything will be reduced down. I mean, the price of the material, the price of the printer, because once they innovated the normal printer, which is for paper sheet, it is also very costly in the beginning, but later on reduced down because we have different manufacturing and we have a lot of competition in the market. So at the moment, I agree. So the printers will be expensive, but when we have more industry trying to develop or to make different printers, so of course these printers will be reduced down, and this technology, actually inkjet 3D printing technology, it is awesome to be printing as a prefabricated, I mean like a precast members, for example, like a precast houses, precast member like a beams, columns, slabs, or staircases, stuff like that. It's pretty awesome to start with this stuff, and I'm sure we'll be reducing down the costs by having too many like companies trying to develop this printer.
Oh, that makes a lot of sense. Thanks you. So it would also, I guess, depend on other industries also pushing. Yeah,
exactly.
3D printing.
Yeah, because now I can see so many other companies like a Perry, which is developing the formwork. They are trying to contribute in a 3D printing technology, but not this technology actually. The another one, which is called extrusion 3D printing. So it means those formwork companies, they should convince themselves and trying to develop new stuff, because they know this is a future for humanity. And basically it is, because you are removing the formwork completely in a like a site work or for construction. So this huge amount of money will be returned back to the companies. So and basically we have a prefabrication for a long time in construction. So from this technique we can get a lot of benefit.
Thank you very much.
Okay.
Are there any other questions? I've unlocked the video and mic.
Yeah, thanks.
Can I ask one, please?
Yeah, sure, Farid. Go ahead.
Like you said, push the one. It's a future of construction from many perspectives.
Yeah.
I've never tried that. So
Yeah.
I had 3 questions. There are
Yeah,
basic
sure.
questions. Definitely your research had gone more deeper into what I'm going to ask. But just to resolve those basic questions for
Yeah.
myself, the first question I have is that how many workers or laborers does it take to operate a 3D printing machine that supposedly is planned to work on site? That's one question.
Actually, as a technical, so you may need only one.
One person.
But someone it should be skilled labor. Actually, we can have a labor, but basically we should develop them with that, or we can say we can teach them properly how we can use the 3D printer. And I think those institutes that we have, like a TAFE or other colleges, it can be using the 3D printing in their mind to help those people, to help the skilled people, and one skilled engineer as well. So one skilled engineer and one skilled technician, it will be proper to be used 3D printer.
Okay. So that's a lot of points in that perspective.
Yeah, it depends. That's it.
Working
Actually,
and
this is it.
operating the system.
I agree. It depends on the how is the scale of the manufacturing. So this is I'm just talking about maybe just 3x3 or 4x4 meter scale of this manufacturing. But if you have a multiple, so that times you need to multiple printers. So that times you need to duplicate, or you need to consider all those perspectives. Yeah.
The other question is that, do we have some Australian builders that are using these 3D printers in a real world?
Actually, we don't have it yet in Australia, but in Europe they have been like a PERI, as I mentioned. They are working like a joint venture with
Saw your
Cobalt.
LinkedIn post. One of them was built and occupied by residents.
Sorry.
Saw one of your LinkedIn posts that was about a house that was 3D printed.
Yeah.
Was occupied by residents. So yeah, in Europe it's developed, but still not in Australia.
Yeah, in Europe and US as well. In US they have Icon, so they have been printed few houses in Mexico, and Cobalt, as I aware. So this is joint venture with the PERI, so they are being developed a lot as well. So contour crafting, which is being in US for a long time, so they have been using different technique to print.
Assuming that Australia is planning to get 3D printers in the construction industry, we're probably going to need some standard codes before a proper manufacturing starts. But now the third question is that, do European countries and also America have some standard codes regulated for the use of 3D printers in the construction industry at the moment, so that Australia may look at those for the adoption?
Exactly. Israel, they don't have any like a standard for that, and even Europe and like US as well. So they have been trying to have a committee, different committees, and to try make a standard for the 3D printing technology. But this will be very limited because the technologies that we have, we should consider all different technologies, and it will be suitable for construction for sure. So I'm not sure how they can arrange this like a guideline, we can say, or like a standard in future. So, but I'm aware like there is a different committees like ASTM as well. They invite me for such as a speaker to talk about this technology. So I think they have different committees to discuss in further detail about this technology for 3D printing.
Awesome. Thank you so much.
You're welcome, Farid.
Do we have any more questions today? That's clear. So we actually don't have our last speaker today. It's supposed to be Ashley, but I haven't been able to contact him. So I've tried emailing. So we might just have to wrap up our webinar slightly early today, just by 15 minutes. If anyone has any questions about anyone that presented today, if you're unable to get their email, feel free to email me and I can connect you. And I will also send out the invitation to create an account with us, so you can get your ICM coin. But thank you everyone for joining us today.
Thanks.
Thank you so much.
Thanks everybody else.